Okay, hello folks. We're just going to talk about SUVAT equations, where they come from. So SUVAT, we'll just quickly check that we've got all these vector values here. S represents displacement as in vector form, not distance. A is acceleration, T is time, U is initial velocity, V is final velocity. In this little graph here, basically what it's representing is an object that is accelerating at a constant rate, hence the straight line, from initial velocity of U up to a final velocity of V, and it's taking t seconds to complete that. So that graph is all you need really to derive the 5 SUVAT equations. The first one, the most important one that we'll deal with, is V equals U plus AT. So if I just write it down, where does it come from? Well, the idea with V equals U plus AT is, if we think about this, the velocity we've got here, V, we've got the initial velocity U, the acceleration is the only value we're not seeing on this. So if we think about a velocity time graph, the acceleration is represented by the gradient of this line. So if we think about that, so the gradient of the line, which is A, how are we going to work that out? Well, rise over run, that's the classic that we'll go for. And in this case, the rise of this is going from U to V, so the difference here is V minus U. And the time it's taking, the horizontal is T, there's your run. And so now we've got A equals V minus U over T. So rearranging that gives us AT equals V minus U. And I rearrange one more time by adding on U to both sides and swapping sides. That gives us our V equals U plus AT. So that's the first of the SUVAT equations, the most important one that we will deal with. Second one, nice and straightforward, is S equals a half U plus V lots of T. Okay, this one introduces S, which is displacement. Again, very similar to what we've had before, but if we go back to this initial graph here, the S value, the displacement, is going to be represented by the area underneath the graph, all of this space underneath here. So once we take that into account, that this is all going to be S, if we just turn the page around by 90 degrees, you can see that we've actually got a trapezium shape here. So we've got parallel lines here with U and V. And so how do we work out the area of a trapezium? Well, in simple terms, it's going to be averaging those two values out. So U, add V, find the average by halving them, the sum, and then multiply by the perpendicular height, which in this case will be T. So that's where that one comes from. So it's already there, basically. So S equals U plus V all over 2 times T. The second one you can see just by considering a trapezium. Okay. The third one, which we will deal with, which is slightly harder to show where it comes from, is this one, S equals UT plus half AT squared. Again, if we go back to the graph here, this time what I'm going to do is just split that area in two. So rather than treating it as a trapezium, we're going to treat it as a rectangle and a triangle. So we think about those two areas underneath the graph. We've got UT for the bottom bit here. So it's clear to see where we're getting the UT from. But the triangle bit here, we've got this is T and this is V minus U, which we dealt with before. So in terms of the area of a triangle, half base times height. So we're going to get half T and then V minus U, okay, which is this height here. The truth is, where did we do that? What do we do with the V minus U now? Well, bear in mind the V minus U we've used before, which was AT. And so we swap that in. All we need to do now, UT plus half T, multiply by AT, that gives us UT plus a half AT squared, okay, which is the third of our SUVAT equations that we'll need to deal with. The fourth one, which I'll put over here, you can just still see, is S equals VT. This time it's minus a half AT squared. Not one I use a huge amount of times, you don't need to. But again, all this one comes from, if we go back to the original graph, the velocity time graph, we're still going to work out the area underneath the graph, but rather than treat it as a trapezium or splitting into a rectangle and a triangle, we're going to look at the big rectangle this time and then subtract this triangle up here. So all we're doing there, move back down, to work out this, the VT comes from the total area of the big rectangle, and this time we'll get rid of this triangle, which is the same as this triangle, so we'll be taking away half base times height again, so half t lots of v minus u. Exactly the same as the previous one. We swap the v minus u for an at. And then we can calculate what we need for the last bit. So we get vt minus a half at squared. So that's the fourth of the 5 SUVAT equations we need to deal with. The last one I'm going to deal with is the v squared equals u squared plus 2as. Again, really useful one, we actually use a lot. In case of this one, we don't need to particularly look at the graph for this one, but what we'll do is we'll start with the initial one, the v equals u plus at. We know that to be true, so if we go to v equals u plus at, and we square both sides, we get v squared equals u plus at multiplied by u plus at. And then we multiply out the brackets, that will give us u squared plus 2 lots of uat, and then plus an at times an at, which is an a squared t squared. So now we've already got the start bit of it, we've just got to get this 2as bit there going. So if I factorise these last two bits here, and I just take out the 2a, I'm left with a ut there. And if I take out a 2a, well, there wasn't a 2 there to take out of, so I've got to leave myself in half. I've got rid of one of the a's, so I'm left with 1a and still the t squared. What you can see there is ut plus half at squared. We've used in one of our other SUVAT equations up here. We know that's equal to s, and so u squared plus 2as, and that gives you your final SUVAT equation. Okay, brilliant. And these are the ones that you've got in your formula book, but you will use them certainly time and time again. Okay, thanks guys.